Good evening, everyone. Today, I will discuss on alternators. First of all, let us know what is the basic difference between AC system and DC system. AC system has a number of advantages over DC system. These days, three-phase AC system is being exclusively used for generation, transmission, and distribution of power. The machine which produces three-phase power from mechanical power is called an alternator. AC system and DC system. AC system has a number of advantages over DC system. First of all, let us know what is alternator. AC system exclusively used for generation, transmission, and distribution of power. The machine which produces three-phase power from mechanical power is called an alternator or synchronous generator. Both are same. Alternators are the primary source of all the electrical energy we consume. These machines are the largest energy converters found in the world. They convert mechanical energy into AC energy. They means alternators convert mechanical energy into AC energy. First, let us try to understand in clear sense what is an alternator. Okay, an alternator is a device which converts mechanical energy into AC energy. Conversion of mechanical energy into AC energy. The machine and alternator operates on the same mechanical power called an alternator or synchronous generator. Same. Alternator. An alternator operates on the same fundamental principle of electromagnetic induction as a DC generator. That is, when the flux linking a conductor changes, an EMF is induced in the conductor. Like a DC generator, an alternator also has an armature winding and a field winding. in two vehicles. But there is one important difference between the two. In a DC generator, the armature winding is placed on the rotor in order to provide a way of converting alternating voltage generated in the winding to a direct voltage at the terminals through the use of a rotating commutator. The field poles are placed on the stationary body of the machine. Since no commutator is required in an alternator, it is usually more convenient and advantageous to place the field winding on the rotor part, that is, on the rotating part, that is rotor, and armature winding on the stationary part. Advantages of stationary armature. The field winding of an alternator is placed on the rotor and is connected to DC supply through two slip rings. The three-phase armature winding is placed on the starter. The arrangement has the following advantages of alternator. Anyone having any doubt, please ask me. Advantages of stationary armature in case of alternator. It is easier to switch stationary winding for high voltages for which the alternators are usually designed. It is because they are not subjected to centrifugal forces, and also extra space is available due to the stationary arrangement of the armature. The stationary three-phase armature can be directly connected to load without going through large, unreliable slip rings and brushes. Only two slip rings are required for DC supply to the field winding of the rotor. Since the exciting current is small, the slip rings and brush here required are of light construction. Next, I will discuss construction of alternators. An alternator has three-phase winding on the starter and a DC field winding on the rotor. Different parts of alternator: starter, rotor, salient pole type, non-salient pole type. First, I will discuss on starter. It is the stationary part of the machine and is built up of sheet steel laminations having slots on its inner periphery. That means it has different sections. In case of starter, a three-phase winding is placed in these slots and services and serves as the armature winding of the alternator. The armature winding is always connected in star and the neutral is connected to ground. That means three-phase supply is required in case of alternator. Rotor. The rotor carries a field winding which is supplied with direct current through two slip rings by a separate DC source. This DC source is generally a small DC shunt or compound generator mounted to the shaft of the alternator. Rotor construction is of two types: salient pole type, non-salient pole type. In alternator, rotor is called the rotating part and starter is always stationary. Movement of rotor is being done with the help of starter. Salient pole type. In salient or projecting poles are mounted on a large circular steel frame which is fixed to the shaft of the alternator. The individual pole The individual field pole winding are connected in series in such a way that when the field winding is energized by the DC exciter, adjacent poles have opposite polarities. This means that when movement of rotor starts, opposite, that means south pole will get negative charge and north pole will get positive charge. Okay, let me discuss more. Low and medium speed alternators. Range is 120 to 400 rpm. RPM means revolution per minute, such as those driven by diesel engine or water turbine, have salient pole type rotor due to the following reasons. The salient pole types would cause an excessive windage loss if driven at high speed and would tend to produce noise. Salient pole construction cannot be made strong enough to withstand the mechanical stress to which they may be subjected at higher speeds. Since a frequency of 50 Hz is required, we must use a large number of poles on the rotor of slow speed alternators. Low speed rotors always possess a large diameter to produce the necessary space for the poles. Salient pole type rotor has large diameter and short axial length. From this we can understand that salient poles type play major role in the movement of alternators. Next, non-salient pole type. The rotor is made of smooth, solid, forged steel radial cylinder having a number of slots along the outer periphery. The field windings are embedded in these slots and are connected in series to the slip rings through which they are energized by the DC exciter. The regions forming the pole are usually left unslotted. It is clear that the poles formed are non-salient; they do not project out from the outer surface. Higher speed alternators, 1500 or 3000 rpm, are driven by steam turbines and use non-salient type rotor due to the following reasons. This type of construction has mechanical robustness and gives noiseless operation at high speed. The flux distribution around the periphery is nearly a sine wave and hence a better EMF waveform is obtained than in case of salient pole type. Since steam turbines run at high speed and a frequency of 50 Hz is required, we need a small number of poles on the rotor of high-speed alternators. We can use not less than two poles, and this fixes the highest possible speed. For a frequency of 50 Hz, it is 3000 rpm. The next lower speed is 1500 rpm, 1500 rpm for a 4-pole machine. Turbo alternators possesses two or four poles and have small diameters and very long axial length. Now I will discuss alternator operation. The rotor winding is energized from the DC exciter and alternate. These machines are enlarged just energy converters from they convert mechanical like supplied to supplied. Alternator operation. The rotor winding is energized from the DC exciter and alternate north and south poles are developed by the magnetic flux or rotor poles. Consequently, EMF is induced in the armature conductors due to electromagnetic induction. The EMF, the induced EMF is alternating since north and south poles of rotor alternately pass the armature conductors. The direction of induced EMF can be found by flip hand rule, and frequency is given by F equals to NP by 120. N equals to speed of rotor in RPM, that is revolution per minute. P equals to number of rotor poles. Now let me discuss on frequency of alternator. The frequency of induced EMF in the alternate conductors depend upon speed and the number of poles. That means speed and number of poles play a very important role in case of frequency measurement in alternator. N equals to rotor speed in RPM, that is revolution per minute. P equals to number of rotor poles. F equals to frequency of EMF in Hertz. Consider a starter conductor that is successively swept by the north and south poles of the rotor. If a positive voltage is induced when a north pole sweeps around the conductor, a similar negative voltage is induced when a south pole sweeps by. This means that one complete cycle of EMF is generated in the conductor as a pair of poles passes. One north pole and adjacent following south pole. Only two poles are required. The same is true for every other armature conductors. Number of cycles per revolution equals to number of poles, pair of poles equals to P by 2. Number of revolutions per second equals to N by 60. Number of cycles per second equals to P by 2 into N by 60 equals to N into P by 120. But number of cycles of EMF per second is its frequency. F equals to N into P by 120. N is the synchronous speed and is generally represented by N subscript S, small s. For a given alternator, the number of rotor poles is fixed and therefore the alternator must be run at synchronous speed to give an output of desired frequency. For this reason, an alternator is sometimes called synchronous generator. AC armature windings. AC armature windings are always of the non-salient pole type and are usually symmetrically distributed in slots around the complete circumference of the armature. AC armature windings are generally open circuit type. Both ends are brought out. An open circuit winding is one that doesn't close on itself. That is, a closed circuit will not be formed until some external connection is made to a source or load. The following are the general features of AC alternating winding. Everyone must know the general features of AC armature windings. AC armature windings are generally distributed windings. That is, they are symmetrically distributed in slots around the complete circumference of the armature. A distributed winding has two principal advantages. First, a distributed winding generates a voltage wave that is nearly a sine wave. Secondly, copper is evenly distributed on the armature surface. Breathing is more uniform and this type of winding is more easily cooled. Next, AC armature winding may use full pitch coils or fractional pitch coils. A coil with a span of 180-degree electrical is called a full pitch coil. Full pitch coil play a very important role in alternators. In case of alternators, in this case, the two sides of the coil occupy identical positions under adjacent opposite poles and the EMF generated in the coil is maximum. A coil with a span of less than 180-degree electrical is called a fractional pitch coil. For example, a coil with a span of 150-degree electrical would be called a 5 by 6 pitch coil. Most of AC machines use double layer armature winding. In a double layer winding, one coil side lies in the upper half of one slot while the other coil side lies in the lower half of the another slot, about one pole each for the first one. This arrangement permits simpler end connections and is and it is economical to manufacture. Since most of the AC machines are of three-phase type, the three windings of the three phases are identical but spaced 120-degree electrical degrees apart. A group of adjacent slots belonging to one phase under one pole pair is known as phase belt. The angle subtended by a phase belt is known as phase spread. This phase spread is very important from examination point of view. Everyone must know the definition of phase spread. The three phase windings are always designed for 60-degree phase spread. Winding factors. The armature windings of an alternator is distributed over the entire armature. The distributed winding produces nearly a sine wave and the heating is more uniform. Likewise, the coils of armature winding are not full-pitched, that is, the two sides of a coil are not at corresponding points on their adjacent poles. The fractional pitched armature winding requires less copper per pole and at the same time waveform of output voltage is improved. The distribution and pitching of the coil affect the voltages induced in the coils. I will discuss two winding factors. Distribution factor, also called breadth factor. Pitch factor, second one, also known as chord factor. Distribution factor. A winding with only one slot per pole per phase is called concentrated winding. In this type of winding, the EMF generated per phase is equal to the arithmetic sum of the individual coil EMF in that phase. However, if the coil per phase are distributed over several slots in space, the EMF in the coils are not in phase, but are displaced from each by the slot angle alpha. The EMF per phase will be the phase will be the phasor sum of coil EMF. The distribution factor Kd is defined as EMF with distributed winding divided by EMF with concentrated winding, or Kd can be defined as phase sum of coil EMFs per phase divided by arithmetic sum of coil EMFs per phase. The numerator is less than denominator so that Kd greater than 1. Next, I'll discuss pitch factor Kp. A coil whose sides are separated by one pole pitch is called full pitch coil. With a full pitch coil, the EMFs induced in the two coil sides are in phase with each other, and the resultant EMF is the arithmetic sum of individual EMF. However, the waveform of the resultant EMF can be improved by making the coil pitch less than a pole pitch. Kp can be defined as EMF induced in short pitch coil divided by EMF induced in full pitch coil. Now let me discuss EMF equation of an alternator. Z equals to number of conductors or coil sides in series per phase. Phi equals to flux per pole in Weber. P equals to number of rotor poles. N equals to rotor speed in RPM. In one revolution, that is 60 by n second, each starter coil is cut by P5 Webers. D phi equals to P phi, and everyone know that dt equals to 60 by n. Dt means differentiation of time with respect to n equals to rotor speed in rpm. Average EMF induced in one starter conductor. D phi by dt equals to P phi divided by dt. In place of dt, we will put 60 by n. By solving the equation, we will get d phi by dt equals to P phi n by 60 volts. Since there are Z conductors in series per phase, the average EMF per phase equals to P phi Zn by 60 equals to P phi Z by 60 into 120 F by P. In place of N, we will write in place of capital N, that is rotor speed in RPM, revolution per minute. N will be replaced by 120 F by P. On solving the equation, we will get average EMF per phase 2F phi Z volt. RMS value of EMF per phase equals to average value per phase into form factor equals to 2F phi Z into 1.1, that is equals to 2.2 F phi Z volt. Always RMS value of EMF per phase is in volts. Volts means voltage. ERMS per phase equals to 2.22 F means frequency phi Z volts. If Kp and Kt are the pitch factor and distribution factor of the arithmetic winding, then ERMS per phase equals to 2.22 Kp Kd F phi Z volt. Now I will discuss armature reaction in alternator. When an alternator is running at no load, that is, no load is applied to the alternator, there will be no current flowing through the armature winding. The flux produced in the air gap will be only due to the rotor ampere turns. When the armature is loaded, the three-phase current will produce a rotating magnetic field in the air gap. The air gap flux is changed from the no load condition to full load condition. The effect of armature flux on the flux produced by the field armature turns, field ampere turns, that is rotor ampere turns, is called armature reaction. Armature reaction definition is the effect of armature flux on the flux produced by field ampere turns. That is, rotor ampere turns is called armature reaction of alternator. discuss important multiple choice questions on alternators. Majority of the alternators in use have options are first option revolving AC armature winding, stationary field type construction, revolving field type construction, none of the above. Major, Majority of the alternators in use have revolving field type construction. Next question, question number 2. The starter of an alternator rarely uses dash slots. First option, wide open type. Second option, semi-closed type. Third option, closed type. Fourth option, none of the above. The correct answer is closed type. Question number 3. The field winding of an alternator is dash excited. First option DC excited, second option AC excited, third option both DC and AC excited, fourth option none of the above. The correct answer is DC excited. Question number 4. The AC armature winding of an alternator operates at dash the field winding. First option the same voltage as, second option much lesser voltage than, third option much higher voltage than, fourth option none of the above. The correct answer is much higher voltage than the field winding. The AC armature winding of an alternator operates at much higher voltage than the field winding. Means much higher voltage is required than the field winding in case of alternators to operate. Question number 5. An alternator is sometimes called dash generator. First option synchronous generator, second option asynchronous generator, third option Rosenberg, fourth option none of the above. Everyone must know an alternator is sometimes called synchronous generator as I have discussed earlier. A turbo alternator uses dash. First option salient pole field structure, second option non-salient pole field structure, third option rotating AC armature winding, fourth option none of the above. The correct answer is non-salient pole field structure. High speed alternators are driven by first option engines, second option hydraulic turbines, third option steam turbines, fourth option none of the above. The correct answer is steam turbines. The speed at which a 6-pole alternator should be driven to generate 50 cycles per second is first option 1500 rpm, second option 1000 rpm, third option 500 rpm, fourth option none of the above. The correct answer is 1000 rpm. Next question, the speed at which a 6-pole alternator should be driven to generate 50 cycles per second is first option 1500 rpm, second option 1000 rpm, third option 500 rpm, fourth option none of the above. The correct answer is 1000 rpm. rpm stands for revolution per minute. Next important question, the frequency of EMF generated in an 8-pole alternator running at 900 rpm is first option 50 Hz, second option 60 Hz, third option 120 Hz, fourth option none of the above. The correct answer is reactance of an alternator is generally dash armature resistance 5 times smaller than, 5 times greater than, 10 to 100 times greater than, fourth option 10 times smaller than. The correct answer is 10 to 100 times greater than.